Now, let us understand what is gravitational field. The basic definition of gravitational field is force per unit mass. Let us have a deep understanding about it. There is an object of mass m placed at certain point. Now, as the distance from this increases, the gravitational force of attraction due to this particle will decrease because force is inversely proportional to r square. So, at certain distance from this mass m, the force of this mass particle will be reduced to almost zero value. So, the region around this mass particle m, in which its force of attraction is experienced by another mass particle, is called electric field. The electric field intensity is defined as the gravitational force acting on the unit mass, that is 1 kg mass, of an object in the field of given mass. It is defined as force per unit mass. It is the vector quantity. And its SI unit is Newton per kg. Now, let us see the gravitational field due to different structures. First, due to point mass. The gravitational field due to point mass is simply gm upon r square, where m is the point mass of which we are finding the electric field. Now, the electric field due to spherical shell. Spherical shell is the hollow sphere inside which there is no mass. So, inside gravitational force is 0 and gravitational field is also 0. At any outside point, this spherical shell will behave as a point mass. So, for outside point, the electric field, the gravitational field will be gm upon r square. Now, due to solid sphere, let's say this is a solid sphere of mass m and radius small, radius capital R. First, we will find the gravitational field at a point inside. Let's say it is point P and the distance from center is R. So, for inside point, gravitational field intensity is given by gm into R upon R cube. For outside point, again it will behave as a point mass. So, the gravitational field will be gm upon R square. Now, let us see the relation between gravitational field and potential. The potential is denoted by V. The small potential difference dV is related to field as dV is equals to minus I dot dr. Now, what is gravitational potential? The gravitational potential due to the gravitational force of Earth is the potential energy of a particle per unit mass. So basically, it is the potential energy per unit mass. We can say that potential energy is equals to work done, or changing potential is equals to work done. So, potential will be equal to work done per unit mass. And potential energy can be written as mass into potential. So, V will be equal to, potential energy is given by minus gmm upon r divided by mass, that will be equal to minus gm upon r. Now let us see potential due to different structure. The first one is potential due to uniform thin spherical shell. A thin spherical shell of radius capital R and having mass m is placed. We want to find the potential due to this shell at two different points. One is located outside the point at distance r1 from the center, and the other is located inside the shell at distance r2 from the center. So case 1 for outside point. For the outside point, this whole spherical shell will behave as the point mass object. So, due to this point mass object, the potential at point P will be Vp is equals to Gm upon R1, but minus. Now, at point Q, that is the inside point. So, for inside point, the potential at Q will be minus of Gm upon R. Here R is the radius of spherical shell. Here note that the potential inside the sphere is independent of the location. As we can see in the formula, this is not dependent on the distance from center R2. So it is independent of location. So for outside point, it will behave as a point mass, and for inside point, it is constant. That will be minus Gm upon R. For outside point, potential is inversely proportional to R. So if we draw the graph for potential versus distance, on this axis, this is potential and this is the distance R. The graph will be negative because the potential is negative. This is center, from center up to the surface of sphere, that is up to the point R. This section is inside sphere, and inside the sphere potential is constant. So graph will be constant, having the value minus VQ by R. Now, as we move outside the sphere, the potential is inversely proportional to R. For inversely proportional quantities, the graph will be hyperbola. So the graph will look like this, where potential is inversely proportional to R. Now, let us see the potential due to a uniform solid sphere. Again, and thus we are considering two different cases, one at point P outside and one at point Q inside the sphere. The radius of the sphere is capital R and mass of the sphere is m. For case 1, that is outside the sphere, for outside point, this whole sphere will behave as a point mass. So, the potential at point P outside the sphere will be same as that of point mass, that is minus Gm upon R1. So, we can say that outside the sphere, potential is inversely proportional to r. Now the second case for inside point. The potential inside solid sphere at any point is given by minus of gm upon 2r cube into 3r square minus r square. You can remember this formula as 3223. 32 in numerator and 23 in numerator, where r is the radius of sphere and small r is the distance from the center. For different values of small r, we can get potential at different points. So this is the in general formula for potential at any point inside the sphere. Now let us see different cases for that. The first one is potential at the center of sphere. To find potential at the center of sphere, put small r is equals to 0 in this equation. So we will get V is equals to minus gm upon 2r cube into 3r square minus 0. This r square will get cancelled out. So potential at center will be equal to minus 3 by 2 gm upon r. Now to find potential at the surface. Put small r is equals to capital R because surface is located at the distance is equals to radius from the center. In this equation, put the value. We will get V is equals to minus gm upon 2r cube into 3r square minus r square. That will be minus gm upon 2r cube into 2r square. So potential at the surface will be equal to minus gm upon r. From this two value, we can see that potential at center is 3 by 2 times the potential at surface. This is the very important relation regarding the numerical problems. Now we have seen that potential inside is minus gm upon 2r cube into 3r square minus r square. So we can write for inside point V is directly proportional to r square, and for outside point it is minus gm upon r. So V is inversely proportional to r. So let us draw the graph for potential versus distance for solid sphere. This is potential, this is distance from the center. Remember, it is distance from the center. The potential is negative, so graph will be negative. This is at center C. For inner part, that means up to distance r is equals to capital R, that is radius. V is directly proportional to r square. If V is directly proportional to r square, then the graph will be parabolic. So at the center, its value will be minus 3 by 2 gm upon r. The graph will be parabolic in this region. Now, outside the sphere, the V is inversely proportional to R. So, graph will be hyperbolic. V is inversely proportional to R and the graph will be hyperbolic. And the value of potential at center will be minus Gm upon capital R. Now, let us see the potential due to uniform ring. A ring of mass m and radius r. The distance from a point at which we want to find the gravitational potential is at distance of r from the center. At this point P, we want to find the potential. The gravitational field on the axis of ring is given by I is equals to minus Gm x upon r square plus x square whole power 3 by 2, where x is the distance from the center on the axis. Here now dv is equals to minus of I dot dr. Given I this value, dv will be gmx dx upon r square plus x square whole power 3 by 2. So let us integrate on both the side to find the value of potential. V will be equal to integration of gmx dx divided by r square plus x square whole power 3 by 2 and limits from infinity to x. So the potential will be minus gm divided by r square plus x square whole power 1 by 2. So this is the potential on the axis of ring. Now let us solve an example based on potential and gravitational field. Given the potential at any point is equals to xy plus yz plus xz plus xyz, we want to find the gravitational field at point 1, 1, 1. The relation between gravitational field and potential is given by I is equals to minus del V by del R. So, the x component of a gravitational field will be minus del V by del x, y component will be minus del V by del y, and z component will be minus del V by del z. So let us find all the components one by one. Ix will be minus del V by del x, that is equals to minus of del by del x of xy plus yz plus zx plus xyz. To do the partial differentiation, only x will be considered as variable, all the other are considered as constant. So differentiation of xy will be y plus differentiation of yz will be 0 as both are constant. Differentiation of xz will be z and that of xyz will be yz. Iy will be del v by del y, that is equals to minus of del by del y of xy plus yz plus zx plus xyz. Partially differentiating with respect to y, Iy will be minus of x plus z plus 0 plus xz. Same way, finding the z component, that is minus del v by del z is equals to minus del by del z of xy plus yz plus zx plus xy z. So Iz will be equal to minus of 0 plus y plus x plus xy. Now put the values of x, y, z is equals to 1, 1, 1 and this value of ix, iy and iz. So ix will be minus of 1 plus 1 plus 1, that will be 3. Iy will be minus of 1 plus 1 plus 1, that will also be 3. Same way iz will also be minus 3. So the gravitational field is given by minus 3 I cap, minus 3 j cap and minus 3 k cap Newton per kg. So this will be our final answer. In this example, in certain region, the gravitational field is given by I is equals to minus k by r, where r is the distance and k is constant. If the potential at r is equals to r naught is v naught, then we want to find the expression of potential. The relation between gravitational field and potential is given by I is equals to minus dv by dr, and I is given as minus k by r. So we can write dv by dr is equals to k by r. So dv will be equal to k by r dr. Now integrating both this side, dv is equals to integration k by r dr. The initial position is r naught and at that point potential is v naught. At any arbitrary point r, let's say potential is v. So v minus v naught will be equal to, here k is constant, integration of 1 upon r will be log r, limits from r naught to r. So v minus v naught will be equal to k log r minus log r naught. But in actual it will be ln r. So to convert it into log, we have to multiply it by 2.303. Applying the logarithmic rule, v minus v naught will be equal to 2.303 k log of r divided by r naught. So the expression of potential will be v is equals to v naught plus 2.303 k into log of r divided by r naught. So this will be our final answer. In this example, an infinite number of point masses, each equal to m, are placed at x is equals to 1, x is equals to 2, x is equals to 4, x is equals to 8 and so on. We want to find the total potential at x is equals to 0. This is x is equals to 0, x is equals to 1, x is equals to 2, x is equals to 4, x is equals to 8 and so on. The all mass particles having same mass m. The potential at point x is equals to 0 will be the addition of potential due to all the individual point masses. So the total potential at point x is equals to 0 will be minus of gm upon this distance 1 minus of gm upon this distance 2 minus gm upon 4 minus gm upon 8 and so on. taking minus gm common, so minus gm into 1 plus 1 by 2 plus 1 by 4 plus 1 by 8 and so on. This is the infinite geometric progression. The first term a is 1 and all the subsequent terms are having common ratio. The common ratio r is 1 by 2. So this sum will be a upon 1 minus r, that is equal to 1 divided by 1 minus 1 by 2, that will be equal to 2. So the potential at x is equals to 0 will be equal to minus 2 gm. So this will be our final answer. In this example, a thin wire of length L and mass m is bent to form a semicircle. We want to find the gravitational field at the center. First, let us draw the semicircle. This is the semicircle formed. Let's see. This is x-axis and this is y-axis. We will divide this whole semicircular part into small individual mass particles of length dl. They will subtend an angle of d theta at the center. And so this point is A and this point is B. Let us assume that radius of the semicircular arc is r. So the gravitational field at point O due to this small mass particle will be in this direction. It is always attractive, so it will be in this direction, that is df. In the exactly opposite side, this angle is theta. So in the exactly opposite side, at same angle, we can assume another small mass part of length dl, making an angle theta at this point. So due to this part, the gravitational field at point O will be attractive and that will be in this direction. The magnitude will be same, df. So at point O, there are two fields. This is df and this is also df. If we divide them into components, then this df will be divided into these two parts, and the first one will be along these two axes. We can see the horizontal component of the force will be cancelled out, so the net resultant force will be along the vertical axis only. Let us write the equation. The gravitational force df is equals to gm upon L into r d theta upon r square, and that is located along side OA. So this can be written as gm upon LR into cos theta d theta I cap plus sin theta d theta j cap. So the force can be written as, integrating both the side from 0 to pi, we will get gm upon LR integration from 0 to pi cos theta d theta I cap plus sin theta d theta j cap. So the F will be gm upon LR integration of cos theta will be sin theta I cap minus integration of sin theta is minus cos, so minus cos theta j cap, limits from 0 to pi. Put the limits. Sin pi and sin 0 are 0. So gm upon LR into minus of cos pi plus of cos 0. So force will be gm upon LR. Cos pi is minus 1 and cos 0 is 1. So this will give us the answer 2. And it will be directed along G. So F will be gm upon LR into 2 directed along J cap. But we don't know the radius, the only length is given. So to find the radius, angle is equals to arc upon radius. The total circumference will be pi r is equals to the length. So r will be equal to L upon pi. Put this value in this equation, we will get F is equals to 2 pi gm divided by L square G cap. So this will be our final answer.